तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 14 on our ongoing series on mechanical measurements. Towards the end of the last lecture, we are in fact looking at the nature of errors in temperature measurement, and we just gave a brief description of the kind of lead wire model one uses. And what I am going to do now is to just recapitulate a few of the ideas from that lecture, and then carry on with two examples. One, the thermometer well problem, which will be followed by a worked out example, and then I will also look at the calculation of error due to radiation. So, these two examples will give a flavor of the kind of problems one faces when making measurement of temperature. In fact, in the last lecture we have talked about different situations or various situations where temperature is measured. The temperature may be within a solid, somewhere inside. It may be on the surface of a solid, it may be the temperature of a flowing fluid, the fluid flowing through a duct or a pipe or a tube. And in each one of these cases, there are several paths for heat transfer, and in fact, we identified the general nature of the heat transfer paths or the heat loss paths, and then we discussed that these can be modeled through a proper thermal model, and then we will be able to estimate the systematic error due to heat transfer through various mechanisms. In the next slide, I am showing, just to recapitulate the lead wire model we indicated in the last lecture. We have two wires corresponding to the positive and the negative thermocouple wires, and the two wires are encapsulated in the sheath material, which is insulating, both electrically insulating, that is what we want actually, but it is also going to create give some kind of an insulation for heat transfer also. And the major dimensions were explained in the last lecture. And what we did towards the end of the lecture was to show that the two wire model to the two wire actual thermocouple with the sheath surrounding it is replaced by a single wire model consisting of a single wire of radius R1 surrounded by a sheath of radius, outer radius equal to R2, and we explained how to do that one. And in fact, we also explained that the mechanism of heat transfer will be the following. The wire is a very highly thermally conducting material because it is metallic, and therefore, you have heat transfer in the axial direction in the wire. So, that is shown by this arrow, and in the insulation which is surrounding the wire, in the single wire model we have a single wire surrounded by some certain thickness of insulation, and we have heat flow predominantly in the radial direction in the insulating layer. That means that we are going to model the lead wire conduction as one dimensional conduction along the wire in the axial direction, and the heat flow in the insulating layer in a direction normal to the axis of the wire. So, actually in the radial direction. So, the idea is to look at a typical application where such a situation exists and find out how to make calculation of the heat loss due to conduction, and then see how it is going to affect the temperature which we are going to measure. So, the lead wire conduction model. So, what I will try to do is to give basically the appropriate formulae with some physical justification and not too much of a mathematical derivation, because at this time the students may not have had a course in heat transfer. So, which may come little later. So, this will be just a kind of a physical arguments will be used instead of using mathematical arguments. So, the wire is in this form, and I said that the heat transfer is in the axial direction. This is the wire heat transfer, and surrounding that is our insulating layer, and the heat transfer is in the radial direction in the insulation. This is in the wire and in the insulation. So, we expect temperature variation to be in this direction predominantly, in the axial direction, and this gives rise to heat transfer like what is shown in the by the arrows. So, now the wire will conduct the heat axially, and some of the heat will leave through the insulation like this all along the wire, something like what is shown here, like a tree. The point to notice is that the heat transfer in the radial direction keeps on decreasing, as also the heat transfer in the axial direction. Some amount of heat comes in here and a little bit is going to be lost here, and the rest of the heat is going to flow on in the axial direction. Some amount of heat is going to leave. Therefore, it is a continuous process. We can show in fact that the heat loss in the radial direction through the insulation So, we are going to model this as follows: is due to a temperature difference between the wire temperature, let us say Tw, which is a function of x. If I measure x from some datum here, and then I am measuring x in this direction along the length of the wire, the heat transfer is Tw at x minus the ambient temperature, which I will write as T infinity, that is Tw, which is the value at any particular value of x along the wire. In fact, I will treat this as uniform across the wire. That means that the temperature, any cross section of the wire, if you take, the temperature is uniform across that cross section given by Tw, which of course is a function of x. So, the heat loss in the radial direction through the insulation will be proportional to the temperature difference Twx minus T infinity multiplied by some conductance. So, we will say some conductance. So, the idea is to find out how to evaluate this conductance in the radial direction. So, what I will do is I will just give a formula instead of working out mathematically. So, I will work it out in terms of a resistance for heat transfer. In fact, we can note that if I go here, the conductance can also be looked upon as the inverse of a resistance, because Ohm's law says that potential difference divided by resistance will give you the current. In this case, the current heat transfer is like a current, the temperature difference is like a potential difference, and instead of conductance I can have a resistance in the denominator. So, it is as well if I obtain a resistance to heat transfer, and in fact, we can show that the resistance to heat transfer consists of two components. I will say it is R, the resistance to heat transfer is one due to convection resistance at the surface of the insulation, this is one component, plus conductive resistance in the insulation. In most books on heat transfer, expressions are worked out for this, and we will just take the expression without proof, and this will be given by 1 over the area for heat transfer, which will be 2 pi R2 multiplied by H, the heat transfer coefficient at the surface, plus conductive resistance is given by 1 over 2 pi K I, which is the resistance of the conductivity of the thermal conductivity of the insulating material, multiplied by the logarithm of the ratio of radii R2 by R1. So, the heat transfer in the radial direction is represented by a resistance to heat transfer given by the sum of two parts, the convective, it is also sometimes called the film resistance, which is given by the first expression which is shown here, plus the resistance due to the finiteness of the thermal conductivity of the insulating material, which is given by the second expression here. And if you remember, when we discussed the single wire model for the thermocouple, we had actually obtained relationship for R1 and R2 in terms of the dimensions of the conductor, the two conductors and the insulating layer and so on. So, this is already available to us, and therefore, I can use this expression, these sum of these two resistances for resistance to heat transfer in the radial direction. Now, let me just make a simple sketch indicating what we are going to expect. Suppose we have a wire which is in the form of a long cylinder, because we remember that the wire is usually long, because the thermocouple leads are taken far away and connected to an voltmeter to measure the temperature. Therefore, this is relatively long compared to the radius of the cylinder. Okay. The radius of the cylinder could be a few, at the most a fraction of a millimeter, and the length of this could be even a few meters or at least a meter. Therefore, it is a very long cylinder for our purpose. So, now let us look at only the conductor. I will remove the resistance, I will remove the outer insulating layer, and I am just looking at the wire, what is going to happen to that. At this place, it is connected to the measuring junction is there. So, I will just say that is the temperature of the measuring junction, T subscript T. Okay. And here there is the ambient at a temperature equal to T infinity. And if you look at if I take a small portion of material of the wire, some amount of heat will come from the left side by conduction, some amount will leave in the axial direction, and some amount will leave from the side to the ambient. So, this is actually loss from the surface. So, the conduction coming in, conduction leaving, the loss from the surface. So, the energy balance will give us the appropriate equation to be solved, and I am not going to even derive the equation or even solve the equation. I am just going to give you directly the expression which we have for the heat transfer from the surface. So, the heat transfer is proportional to, so the heat transferred, heat loss by conduction is equal to T t minus T infinity. This is the temperature difference available for heat transfer, multiplied by a factor which we get from the theory of by basically solving the equation governing the problem. And I am not going to solve the problem, I am just going to say that this is going to be shown to be equal to the product of the thermal conductivity area for the thermocouple wire, the two wires together, divided by the resistance, which was again obtained earlier. So, heat loss by conduction is equal to, this is like the potential difference, this is like the conductance. So, product of two things. This Ka product represents the sum of K1 A1 plus K2 A2 for the two wires which make up the thermocouple pair. Okay. This expression comes basically from the solution to the heat transfer problem. So, what we should notice that is that the heat loss due to the wire which is attached to the object whose temperature I want to measure is given by a simple formula. If this heat transfer comes from somewhere, okay, that amount of heat transfer from whatever is attached to whatever the thermocouple bead is attached to, the amount of heat it acquires must be exactly equal to the heat lost by conduction. That will give some kind of a relationship between the various temperatures which are involved. Let me take just a simple example which was earlier shown in the previous lecture. So, let me just take a simple typical example and see what is happening. So, we have a heat collecting pad. I indicated the copper disc in this case, a thin copper disc to which the thermocouple junction is attached. So, the thermocouple conduction due to thermocouple which is attached to the back is modeled according to the equation I just now indicated on the board, which is proportional to the temperature of the junction minus the temperature of the ambient here multiplied by that factor. Now, suppose I look at the other side, that is on the other side of the copper disc in this particular case, the copper disc has got some area of the surface equal to S, which is exposed to the fluid which is maybe flowing on this side. Okay. Suppose I assume that the heat transfer coefficient for heat transfer by convection from this fluid to the surface is given or known, then I can find out what is the temperature, what is the heat transfer to this surface from the medium which is flowing by simple expression which is given by the heat transfer coefficient times the surface area exposed to the flow multiplied by the temperature difference between the fluid which is flowing and the temperature T t. Okay. So, I will then equate this to the heat loss through the thermocouple junction, through the thermocouple wire, and I will get an expression between the temperature of the fluid T f, the temperature of the junction which is now indicated by the measurement, and the ambient temperature T infinity. Therefore, if two of them are known, the third one can be determined. So, let us just look at this situation by going back to the board. So, I will make a simple sketch so that we have the heat collecting pad. Let us assume that the surface area is S and there is a fluid which is flowing here at a temperature equal to T f, and the heat transfer coefficient is, let us say, H f, so that it is demarcated from the other one. And now I have the thermocouple attached to the back. This is thermocouple, and this is modeled with T infinity, and of course, a resistance R. We have already done that earlier. Therefore, I can now write a heat balance under steady state when nothing is changing with respect to time. Steady state means no changes with respect to time. The heat acquired by the surface is Hf multiplied by the surface area. This is by definition of the heat transfer coefficient, H into area into temperature difference Tf minus T subscript T, which is the temperature indicated here, that is Tt. This must be equal to the expression we wrote down just a little while ago. It will be given by Ka product divided by R multiplied by Tt minus T infinity. Okay. So, I can now solve for the temperature indicated by the thermocouple. There are two factors. So, you can see that I can transpose. So, Tt multiplied by Hfs plus square root of Ka by R is equal to Hfs into Tf plus square root of Ka by R into T infinity. Or I can take this to the denominator, and I can therefore write Tt equal to finally Hf into S into Tf plus square root of Ka by R into T infinity whole divided by Hf into S plus square root of Ka by R. This expression indicates that the temperature indicated by the thermocouple, that is the left hand side, this is what is measured, is a weighted mean of the temperature Tf, the weighting factor being Hf into S. So, this is the weighted mean of Tf multiplied by the weight factor Hfs plus the weighted mean of Tf with this factor T infinity with the factor square root of Ka by R. That means, I am not going to get either Tf or T infinity, depending on of course the particular case. I will get a temperature which is the mean of these two, with the weights being given by Hfs on the one side and square root of Ka by R for the other side. So, you can immediately see that if this term Hfs is very large compared to this term, if this is very large compared to this term, Tt will be close to Tf. So, that is what we would like to guarantee or find out or make sure that the temperature measured by the thermocouple attached to the surface is going to actually indicate more closely the temperature of the fluid rather than the temperature of the ambient, which is at the back. That means, that if I reduce this term, this factor, if I am able to reduce by the proper choice of the insulating material and so on, and also making sure that there is not too much of convection on the at the back side, and if I make sure that this product of Hf into S, if H is not very large, if I make S large enough, then this product becomes large enough. Therefore, the idea is to increase the product of the heat transfer coefficient on the fluid side and the area of contact between the fluid and the solid. If I increase it, then I will be able to approach, in other words Tt will approach Tf. And in fact, we can say that the temperature difference between Tt and Tf is actually the error in this particular arrangement. So, we want to minimize the error, you have to increase this factor as compared to this factor. That is what the analysis shows. I am not going to work out any problem, just to get a physical idea we have tried to look at this problem. Now, we will go back to the slide which we were looking at and take an example which is very common in practice. In fact, I have already referred to this earlier, that we use a thermometric well or a thermo well in applications where we are measuring the temperature of fluid which is flowing inside a tube, and we would not like to have a contact between the measure sensor which we are going to use, maybe a thermocouple or maybe some other thermometer. We do not want to have a direct contact for some reason or the other. Then we have no option but to use what is called a thermometer well, and the design of the thermometer well is an important aspect when you want to minimize the error between the temperature indicated by thermocouple and the temperature of the fluid whose temperature you want to measure. A typical example is a steam carrying pipe, which is very common in process applications. The steam may be at a very high pressure, maybe hundreds of bars. So, we cannot have a direct insertion of the thermocouple, because that will lead to leakages and other problems. Therefore, a thermometer well is built into the system and the thermocouple is attached to the bottom. In fact, we have already seen this kind of an arrangement, and we indicated the main physical and thermal parameters which are going to play a role in this. So, I have taken a simple example. Through this example, I am going to just look at how we are going to get the thermometer error in this particular case, and also we will be able to decide what are the parameters which are important or which have to be chosen properly, so that the temperature error is minimized. So, we have air at a temperature of 373 Kelvin flowing in a tube of diameter 10 centimeters, and its average velocity is measured, and it is equal to 10 meter per second, and the tube walls are at a slightly lower temperature, in this case 353 Kelvin, and a thermometer well whose outer diameter is 4 millimeter and whose wall thickness is 1 millimeter and made of aluminum. Just an example, aluminum may not be the most suitable material. We just want to indicate how the calculation can be done. Is immersed to a depth of 5 centimeters, that is half the diameter of the pipe, and it is inserted perpendicular to the axis, and we would like to find out what is the temperature indicated by a thermocouple that is attached to the bottom of the thermometer well. Ideally speaking, we would like to have the temperature indicated equal to the temperature of the fluid, which is 373 Kelvin. Anything different from that is certainly an error. And let us look at what is going to happen in this case. We have the 373 Kelvin is the temperature of the fluid, and the wall is at 353 Kelvin, and the thermometer well is connected between the fluid and the wall, and therefore, there is heat transfer from the fluid to the wall through the well, and therefore, this is basically a conduction error problem. And the heat transfer to the well is by convection from the fluid, and the heat loss to the wall is by conduction through the well material. So, with this background, let us just look at what are the things involved. In fact, I am going to go back to the board and indicate some of the details. Just to recapitulate, we have the wall of the tube, and this is the axis, and I have the well right down into the middle. It is made of a material with a certain wall thickness 1 millimeter, and this is 4 millimeter diameter, if I call it D0 outer diameter, and the wall thickness is 1 millimeter, and this depth of immersion is 50 millimeters. Let me just go back and see whether that is 50 or I think it is 50. Yeah, tube diameter is 10 centimeters, and therefore, indeed it is equal to 50 millimeters. This is 100 millimeter diameter, and the wall is at 353 Kelvin, and the fluid is at 373 Kelvin, and the velocity is 10 meter per second. So, let me just draw a simple sketch of the well slightly magnified. so that we can look at what is going to happen. So, I will just draw this is the well with its thickness shown here, fluid is flowing 10 meter per second, and this is the thermocouple attached here, T subscript T. On this side it is connected to the wall at T W equal to 353 Kelvin. So, here T F is 373 Kelvin. So, there is a 20 degrees difference. So, the surface of the tube, outer surface of the tube, suppose I take a look at a small piece of the tube again. Okay, I look at this small piece of the tube. The heat is gained by convection. So, this is convection, and because the temperature is varying in this direction, being higher here, T F is higher, possibly the temperature of the well is in between these two, in between 373 and 353. Therefore, there is heat transfer from here to the well material, and then there is conduction along in this direction. The model is exactly similar to what we had earlier in the case of the lead wire model. There is no difference really. The only difference between the lead wire model which we had earlier and this case is that the lead wire was of infinite length or very large length. Therefore, we had a simple solution to the problem. Here we have a finite length for the immersed well. This L is given from the wall to the depth here. This length is a finite quantity, finite length. So, the Gorning equation is somewhat similar to the previous case, and again I am not going to go through the calculation procedure. What I am going to do is just to indicate how to make the calculation. The heat transfer coefficient or heat transfer from the fluid to the outside of the cylinder is treated as cylinder in cross flow, and the heat transfer coefficient depends on some specific parameters. The heat transfer depends on the Reynolds number based on the diameter of the tube, outer diameter of the tube, outer diameter of the well, and then it depends on the fluid properties. In this case, of course, we have air flowing across the tube. Therefore, the properties of the air are going to come into the picture. Of course, Reynolds number itself contains the property of the fluid going into that calculation. This relationship between the convective heat transfer coefficient and these properties or these number parameters comes from a knowledge of fluid mechanics, and the student will certainly learn these things a little later stage in the course on heat transfer. But right now what we will do is we will simply assume that this amount of knowledge is available in the form of a simple recipe. Okay. So, recipe will be usually represented as a correlation. Just for calculation purposes, it is not necessary to know exactly how the things come out, but it is enough to understand the correlation and get a working knowledge, so that we can just make some calculation. That is the idea with which we are doing this, we are presenting this material now. So, with this, let us look at the details of the problem. So, we have to calculate the heat transfer coefficient on the outside, which is calculated based on the properties of the fluid and the velocity of the fluid which is given, the temperature and so on. So, what are the properties we require? We require to calculate the Reynolds number. It is defined as the velocity u multiplied by the diameter of the tube. When I say the tube, it is the well I am talking about, outside diameter of the tube which makes up the well, and the viscosity of the fluid which is moving. This is the kinematic viscosity nu, and from the tables of air properties we take these values at a temperature. In this case, the temperature of the fluid is 373, the wall temperature is 353. So, we will for the sake of taking the values of the properties at the intermediate temperature in between at the average temperature between these two, that is good enough for this purpose. So, the value of viscosity is 23.02 in 10 to the power of minus 6 in meter square per second. Then the thermal conductivity is 0.03127 watts per meter Kelvin. The Prandtl number is a parameter which describes, is one of the properties of the fluid which comes into the picture when you have heat transfer calculations being done. So, it is equal to 0.7 in the case of air, and the diameter outside is going to come into the picture. It is 4 into 10 to the power of minus 3 meters. I am converting millimeters to meters, and u is 10 meter per second. Therefore, I am able to calculate the Reynolds number as the product of ud naught divided by nu, which is 1.738 into 10 to the power of 3 or 1738. The value of the Reynolds number, the Prandtl number, so on, we will have to put into this recipe I talked about, the correlation. It is called the Zukowski's correlation. I think there is a spelling mistake here. It is Zukowski's correlation. For cylinders in cross flow, the information is represented in the form of a relationship of the form NUD. This is called the Nusselt number. Is given by a constant C multiplied by Reynolds number to the power of m, where d is the characteristic dimension. In this case, it will be d0. Prandtl number to the power of n, and then a ratio of PR by PRS to the power of 0.25, where S stands for the surface temperature. In the present case, these two are close to each other, therefore, this factor is not important. Only for those fluids where the Prandtl number is a strong function of temperature, we have to worry about this factor, and therefore, for the present this factor is not going to come to picture. There is all properties are taken at the film temperature, which is nothing but the average between the surface temperature and the fluid temperature, excepting the one here which is taken at the surface temperature. But in this present case, we need not worry about this factor. The values of C and M and N are specified in the table which is given below. These are all based on experimental data. Experiments have been conducted with cylinder in cross flow with different Reynolds number ranges, and the relationship has been plotted, and using the methods we have already discussed earlier, curve fitting and so on. Based on the curve fit, values of C, M and N have been obtained. So, there are several ranges of Reynolds number 1 to 40, the values are 0.75 and 0.4, 40 to 1000, 0.51 to 0.5, 1000 to 2 lakhs is 0.26 and 0.6, and 2 lakhs to about 1 million it is 0.076 and 0.7. Why do we have different values for different ranges of Reynolds number? Because Reynolds number determines, the range of the Reynolds number determines the type of flow which is taking place, the regime of flow which is taking place. We have essentially laminar flow for very low velocities or very low Reynolds number, and as the Reynolds number increases, the flow becomes more and more, it goes towards turbulent flow, and there are variations from laminar flow to turbulent flow through a series of steps like this. So, the reason why we have different values of C and M is because the regime is changing slowly from laminar flow to fully turbulent flow, and that is represented by this kind of a data. And if you remember in the last slide, we calculated the value of the Reynolds number to be somewhere in between, it was some 1700 and something. So, it comes in the third row here, and the n values are given by for Prandtl number less than 10 and greater than 10, and this is appropriate for the present case because Prandtl number is 0.7 in the present case. And for the range of Reynolds number, the Reynolds number being 1730 or something like that, the value of C and M are given here as 0.26, 0.6, N is 0.36 because Prandtl number is less than 10. So, the Nusselt number based on the outer diameter of the well is given by the product of C 0.26 multiplied by Reynolds number which was already calculated to the power of 0.6 Prandtl number 0.7 to the power of 0.36, and that gives you 20.1. This Nusselt number is a non-dimensional parameter. It is also called a non-dimensional heat transfer coefficient, and the relationship between the heat transfer coefficient and Nusselt number is such that heat transfer coefficient is equal to Nusselt number multiplied by the K of the fluid divided by the diameter or the characteristic dimension in this case, which is equal to D0. And if I substitute 20.1 here, K is 0.03 something, which was given in the first slide, divided by 0.004, I get a value of H equal to 157.13 watts per square meter Kelvin. So, we have calculated the value of the heat transfer coefficient. Now, what we have to calculate is what is called the fin parameter. The fin parameter appears in the solution to the problem when you model the heat transfer in the wall of the well. The heat transfer by conduction is in the axial direction, and the heat transfer by convection is in the direction normal to the axis of the cylinder or axis of the well. In this case, we can show that the governing parameter for heat transfer in the fin is given by m subscript f. This is called the fin parameter, which is given by h into the perimeter, which is pi d0. Pi d0 is the perimeter, outer perimeter of that well material, divided by the thermal current of the well and the area of cross section of the material of the well. It is given by pi into d0 squared, the inner diameter squared, outer diameter squared, minus di squared, which is the inner diameter squared, divided by 4, actually comes from pi d squared, pi into d0 squared minus di squared by 4. This 4 is coming from this. So, it is actually h into the perimeter divided by k into area of cross section, whole raised to the power of 0.5, and if I substitute the values I have obtained earlier, I will get a value of 31.989. And the non-dimensional governing parameter for the fin is given by the product of the fin parameter which is calculated earlier and the depth of immersion. So, the depth of immersion is making its appearance in this parameter, and if I put L equal to that is 50 millimeters, 0.05 meters. So, 0.5 multiplied by the value which was there about 31 in the previous case, I get a value of 1.599. And again it can be shown from the heat transfer calculation that the non-dimensional temperature theta T. So, let me just go back to the board and discuss the temperature. So, we have a non-dimensional temperature function defined we can define in various ways. One of them is equal to T minus Tf minus Tw minus Tf. That means that the value of this theta is equal to 1 at the place where the well is attached to the tube, and it is equal to 0 as far as the fluid is concerned. This varies between 1 and 0. So, what I want is this theta is a function of the position along the fin. So, there is a function of x measured, in this case the L is like this, I am measuring x. Either I can measure it from here or from there, it does not matter. So, it is measured like that. So, with this background we can prove that the value of theta subscript T, this is the temperature at the bottom of the well, is given by 1 over cos hyperbolic mu f, and if I put this 1.59 here, I get a value equal to 0.388, and using the information which I just presented in the board, the temperature of the indicated by the thermocouple attached to the bottom of that well is T reference, which is taken as the temperature of the flowing fluid Tf plus theta T into Tw minus Tf. Okay. So, if I substitute these values of theta T 0.388 here, Tw is 353, Tf is 373, I get a value of 3 subscript T equal to 365.24. So, the temperature indicated by the thermometer, which is connected, or the thermocouple connected to the bottom of the well, is not equal to the temperature of the fluid, but it is 365.24, almost about 8 degrees different. So, we can now say that when we measure the temperature as 365.24, the actual temperature of the fluid is 373. The thermometer error or the systematic error due to the measurement is 365.24 minus 373, which is the difference between these two. So, if I want to use this particular arrangement for the measurement of temperature of a fluid flowing through a tube, I will have to use this as a correction to the measured value. So, because I am going to measure this value, this is what the temperature is indicated by the thermocouple. So, I am going to add this thermometer error, which is calculated based on this kind of an analysis, and correct for the temperature. So, the next example I am going to take is going to be slightly different, and I am going to look at the error due to radiation. So, the problem occurs like this. We have already indicated this earlier in the lecture number 13 in some not too much detail. Suppose I have a tube carrying a fluid and have the, let us say this is the probe, this is the wall which is at a temperature less than the fluid temperature. Radiation loss will be there from the probe to the wall, and there will be convection from the fluid to the surface of the probe. Again you will see that if I ignore, there will be conduction here in general. This is ignored, ignore this, because usually the wires connecting the probe are very small in diameter, and therefore, the conduction may not be very significant or important. Then all I have to do is the analysis is going to be balancing the convective heat transfer from the fluid to the surface of the probe by the loss due to radiation from the surface, and the loss due to radiation from the surface depends on the emissivity of the surface, which I will indicate as epsilon. Actually, if you write the expression for the radiative loss, it will be given by epsilon sigma, sigma is the Stefan Boltzmann constant, multiplied by the surface area, which we will say S is the surface area of the probe, multiplied by T to the power of 4 of the sensor minus T W to the power of 4. This must be equal to the heat transfer coefficient by convection multiplied by the area of surface, which is again equal to S, multiplied by Tf minus Ts, and this S will cancel off, and you see that the temperature of the surface sensor now is going to be governed by this expression. So, the sensor temperature is given by this expression. Now, in actual practice, what is going to happen? I know the reading of the instrument, therefore, Ts is known. This is also known. This is also measured by possibly embedding a sensor in the wall of the tube. So, this is also measured and known. Therefore, I can obtain Tf can be calculated. Actually, what will happen is, I will show it in the next here, Tf minus Ts equal to epsilon sigma divided by h. I am just rewriting the previous expression, Ts to the power of 4 minus Tw to the power of 4, and this is your thermometer error, thermometric error due to radiation. So, it is a straightforward problem. So, the magnitude of this term, the larger the value of epsilon sigma by h, the larger is the thermometric error. So, how can I decrease the error? That is the question I would like to ask. The way to decrease the error is reduce epsilon. So, I will say reduce epsilon. Epsilon is the surface property. It is well known that if you have a highly polished metal surface, for example, aluminum, epsilon could be something like 10.05. So, I would be well off if I have a polished surface, metal surface for the sensor. I would also like to have increase h, and h we know already, that depends on the Reynolds number, and how do we increase Reynolds number? Increase u. In fact, if you remember, in lecture number 13, I indicated that the u can be increased by actually having some kind of an arrangement in which the fluid is accelerated and flows past the sensor at a higher velocity than it would do otherwise. You could have some kind of a small converging diverging nozzle, and the sensor can be within that, and in fact, the advantage of such an arrangement is that there is a radiation shielding also is going to come into picture, because the converging diverging nozzle can be made out of material which is highly polished material made of metal, so that the emissivity is small, and at the same time it accelerates the fluid to a higher velocity, and therefore, the Reynolds number increases, and when the Reynolds number increases, the heat transfer coefficient increases. That means that either decrease epsilon or increase h, we are going to have an effect of reducing the thermometric error by radiation. So, I think I just have enough time to take the example and look at that. So, the example number 15, a thermocouple is made of very thin wires is attached. I have said very thin wires so that the conduction through the lead wires can be ignored, and it is to a spherical shell of 0.005 meters placed inside a large duct whose walls are at 450 Kelvin. The flowing fluid is air at 500 Kelvin. The velocity of air has been estimated to be 0.5 meter per second. So, we want to determine the thermocouple error, and two cases are taken, one in which the emissivity of the surface is 0.05, and the second one in which it is 0.85 in the second case. So, we will quickly go through this example. Again, the air properties are taken at the mean value as we did in the previous case, and the values are taken at 475 Kelvin, 450 and 500. These are the two limits. Nu is 34.09 in 10 to the power of minus 6 square meter per second, K is 0.0489 watts per meter Kelvin, all in SI units. U is 0.5 meter per second, that is given, and the diameter is 0.005 meter, and it is a spherical bead like structure, a spherical sphere, over which the flow is taking place, and we can use a simple relationship between Nusselt number and Reynolds number, just like what we did earlier. This relation is recommended by McAdams. It is valid from 17 less than Reynolds number to 70,000, and it is taken from the book by Holman, which is a very popular book. Nusselt number equal to 0.37, Reynolds number 0.6, or if you put the value of Reynolds number calculated earlier, you will get a value of 4.87. And from Nusselt number, we again calculate the heat transfer coefficient Nu K by D. This is the general definition, H equal to 47.61 watts per square meter Kelvin, and we will go to the two cases. The data for case A, the thermocouple indicates the equilibrium temperature, wherein the heat transfer from air to sphere is equal to the heat loss from the sphere to the air ground. It is just what we explained on the board. Epsilon is 0.05, sigma is 5.67 10 to the power minus 8, which is the Stefan Boltzmann constant. Let the thermocouple temperature, we do not know, we have not been given the temperature indicated by sensor. In this case, the sensor temperature is to determine. I will say T subscript Tc equal to 470 as a starting point. Then the fluid temperature is 500 and the background temperature 450. These are already given, all in temperatures in Kelvin. And when we are calculating radiation, anything to do with radiation, you have to use the temperatures in the Kelvin degrees. And I have to solve the equation H into T of fluid minus T of Tc minus sigma epsilon into T T to the power 4 minus T background to the power 4. This solution can be done by Newton-Raphson method, and I get a value of 498.757, which is rounded off to 498.8, and the thermometer error is only 0.2. When epsilon equal to 0.05, the error due to radiation is negligible. However, in the case B, when all I do is to change epsilon to 0.85, all other things are the same, and then I solve again the same equation, I get a value of 485.34, and the error is almost equal to 15 degrees, 14.7 Kelvin. So the radiation error is very significant. So when do you get a value of 0.85? For example, in practice, if you start with a very highly polished material, and if it is in service for a long time, and the surface gets oxidized because of the flowing fluid and the impurities in that and so on, the emissivity will degrade with time. Of course, it may not degrade up to 0.85, but certainly there will be degradation, and therefore, if you want to keep the radiation error under check, periodically the surface must be cleaned and polished again and again and put back to service. So the observation from this particular example is that surface emissivity as a sensor plays a very important role in this particular case. So in the last two lectures, lecture number 13 and lecture number 14, we have looked at the systematic errors in measurement of temperature under various situations. In the lecture number 15, we are going to look at the measurement of temperatures which are varying with respect to time. The transient temperature measurement is what we are going to look at in the next lecture. Thank you.